Swayam Prabha. Digital India. Educated India.
Good morning, welcome you all to this next lecture in this course on analytical, spectral and microscopy applications of inorganic compounds and nanomaterials. We have looked at just prior to this 4-5 lectures we have spent on the absorption spectroscopy, which is nothing but electronic absorption spectroscopy. Now we know that when the light is absorbed, the electronic transition takes place. That is where we looked at the electronic absorption spectrum. Now that electronic excited state, what happens to that? And that is what is we are going to learn in this emission spectroscopy or fluorescence spectroscopy or luminescence spectroscopy, all of these kind of things. So we will look at these aspects of it. So as I mentioned that please have a look at this particular slide. I talked to you in the previous topic under the absorption spectroscopy, electronic transition from a ground electronic state to an excited electronic state, and what is absorbed and then transmitted is measured, and thereby we had done a lot of work on that, a lot of examples on that, how to find, quantify many things aspect. Now so once the energy is absorbed, the electron is excited from the ground to the excited electronic excited state. What happens to that? So this excited electronic state does not stay permanently there, and it returns back to the ground state, and if that returning to the ground state releases the radiation, then we call it as a emission process or the fluorescence process, and the fluorescence related process I will explain you just in a while, all of that. And those which you cannot see in the form of light, they are lost in the form of heat energies. We will look at that as well. Now I am sure you are aware of this particular kind of a diagram when you have studied your basic electronic transitions. It is called Jabelon scheme. So next few minutes I will be focusing on this particular slide. Please keep your view on the slide itself. So you have one can visualize the energy axis, which is Y, as the ground electronic state, the first excited electronic state as S1, second excited electronic state S2, etc. So these are the things, and each electronic state, as we know very well, are further subdivided into vibrational, and the vibrational is subdivided into rotational, but which we will not look at here, but up to the vibrational. So this 1, 2, 3, 4, 5, etc. this refers to the vibrational quantum numbers of this corresponding under this electronic. Similarly, under the excited electronic state, you again have the sub levels, which are again the vibrational levels. Now when the electronic transition takes place from the ground to excited, it could take to the S1, it could go to the S2 depending upon the molecule, energy supplied, all these kinds of things. Then it could go to any of the vibrational level of the excited state. For example, some molecules may be in the 0 of the excited electron, first of the excited electron, second, third, etc. Now these excited vibrational states can release their energy through internal kind of a conversion process by various kind of a collisions, etc., and then lead to the ground vibrational state of the excited electronic state, that is S1. So from there, if it is returning back to the different vibrational states, the ground state, and that's if it comes in the form of the radiation, then that will be a fluorescence. So in other words, the fluorescence occurs when the excited electronic state of the ground, that is vibrational 0, gets populated. So all the higher populations will return to this without giving any radiation, that is radiationless, and then from this state you have the energy release, and that energy release is measured in the form of the fluorescence. If you have higher electronic states being populated, and these higher electronic states can get turned to the first excited electronic state by again the internal conversion, which will not be seen in the form of radiation, but it will be in the heat energy. So, such kind of a transitions, you can call it as a vibrational relaxation in one way, or internal conversion. These all happen at a rate 10 power minus 11 12, which is pico, to minus 14 minus 15 femto. So, pico to femto level, so 10 to the power of minus 11 to about 10 to the power of minus 14 or minus 15 femto. So, picosecond to femtosecond. So, that is the picosecond to femtosecond. So, this kind of a processes, so they are very fast. On the other hand, whatever comes from the ground vibrational state of the excited electronic to the ground excited electronic state generally happen in the range of 10 power minus 6 to about 10 power minus 9, a little either side. So, this is the micro to nanosecond. So, micro to nanosecond. So, this is much slower than this one. Okay. So, therefore, this can happen quite quickly before the measurements can take place. So, the internal conversion, vibrational state relaxation, all this can happen at a very rapid scale, and as a overall you refer it as a internal conversion process. Then you have the next thing is coming from the first excited zero vibrational state of the first excited electronic state to that of the ground electronic state, any vibrational state here, and that is happens within the microsecond to nanosecond kind of a range. So, this is much slower as compared to this. You can see that the process is very fast and somewhat slower process of this. There are few other processes are also possible at times due to certain other kinds of reasons. The one which is in the populated in the ground vibrational of the excited electronic state need not emit in the form of light, but still can come to the ground state. So, that means the excited state can come to the ground state without giving even the light, and that is again is by the heat, and this process will also go somewhat faster. So, this you can call is a quenching process, internal conversion, whatever the kinds of things can also happen. That means the fluorescence emission is challenged by all the other internal conversion, quenching, all these kind of processes. Additionally, there is one more is there here. These are all singlet electronic state, and you also have a triplet electronic state, triplet the spin state of this electronic state, and this conversion is as such not the allowed kind of a transition, but still can happen. So, that is referred as the intersystem crossing. So, that can happen when you have a kind of a the coupling taking place, spin with the orbit kind of a coupling taking place, and this kind of a transition can take place. In such a case, the emission can occur from this state, which is the triplet state, not the singlet state, to the ground singlet state, and so this process is called the phosphorescence process, and this comes in something like 10 power minus 3 or minus 4 to about a few seconds kind of thing. Okay, and that is a much slower process. So, this is another process that can compete with that fluorescence. So, the fluorescence process is competed by the internal conversion, quenching processes, intersystem crossing, all of these, and then you have. So, that means when you are looking at a molecule, when you excite, in principle you should see if any of these processes are competing with the fluorescence and the fluorescence is getting quenched. So, I hope you are having a look at this particular slide and then to understand. So, this is what is called the excited state coming to the ground state via various different processes. So, excited state has got always higher energy, and the higher energy is lost in various forms. One is by the heat form, other is by the light, and the light that what you are measuring from the ground vibrational of the excited electronic to any vibrational of the ground state of the electronic state. So, I hope that process is understood, and all these processes are referred as the relaxation. So, during the relaxation any of these, all of these, many of these can happen simultaneously together, okay, and then at the end you look at this process of it. Now, so what is the efficiency of that? As we said that we have so many other processes. I will come after a while to explain these other processes, other rates which are competing with the fluorescence rate. So therefore, the photo or fluorescence efficiency is number of photons that are emitted for a photon that is being absorbed, okay. So the photon emitted by photon absorbed, that will give you the fluorescence. If you have many other processes are competing, then that value will be much lower than 1. So if you want to have a percentage, you multiply with 100, so you will get the quantum yield in terms of the percentage. Efficiency, yield, all of these are same terms which you are using one for the same. Okay, so let us look at whatever I mentioned to you using the Jablonski diagram. Now look at some kind of a classical way of looking at it. So classical way of looking at it is, you have your vial, you have your solution, you have your sample in this. Now what you are doing, you put your light on this, so light can pass through, this is the transmitted light, and then light can be scattered through, and light can be reflected. So you can have a scattering process, you can have a reflection process, you can have a transmission process, and you can have an absorption process. By that, that is why remaining thing comes as a transmission, which I explained this phenomena in the previous classes when I started the absorption spectroscopy, same principle. But now for the process of emission, so what you need is, you have to avoid all the reflections, you have to avoid all the other kinds of scattered kind of thing. So but you need to take the ones which is coming the maximum, the beam that comes into the particular light in this direction of the perpendicular with respect to the beam is the kind of that scatter radiation, okay, that is the radiation which comes from the emission part of it. So all other radiations are more affected by the transmitted light, reflected light, other kinds of scattering processes. So therefore, instead of in the fluorescence in the absorption spectroscopy where your detector to the incident light is 180 degree, here it is a 90 degree. So you can see that you have your sample, you have your light, and light incidenting and sample, many things happen here, but your detector is here, this is your detector, and this angle is 90, you can see that. So this is called excitation direction, this is called emission direction. So the excitation emission direction are normal to each other, and that's what. So that is where, why you are looking at, number one, the radiation coming in that is better, the emitted light is maximum here, and this is free from the scattered light, free from the reflected light, free from that the transmitting light. So the transmitted light, scattered light, and the reflected light will be less in the direction of 90 degree, so only the emission comes. Emission will come in other directions as well, but the maximum emission will come in this. So therefore, in the fluorescence, the first and foremost is that you have a 90 degree angle that you are looking at this. Okay, so having understood that the emitted light you are looking in the direction of 90 degree, so that means you can see light source, some kind of a monochromator, your sample, and then the light coming out in this direction. Light comes out in various directions, but you are looking at 90 degree, and then monochromator again, and the detector, and this part is your 90. Please have a look at the slide, I mean showing on the slide all this. Now you can have a single beam, you can have a double beam kind of thing, okay. So for example, you have your lamp, xenon lamp giving the light, and then use your monochromators, gratings, etc., and then the light coming through this and goes into your sample. Now this is the direction of your light here, so and then so you should measure in 90 degree this direction. So therefore you arrange your the optics in a 90 degree fashion, so that your light which is coming in the 90 degree, that is the emitted light, only in that 90 degree direction will be captured, and this will be converted by various these things and then go to the multiplier. So photo multiplier will give you the detector. On the other hand, you can take this beam and close this direction, take to the other direction where you have your reference. So you can do the same kind of thing with the reference as well. So that is what is called the double beam spectrometer. So, I hope you understand the principle why we are measuring in 90-degree, unlike in the absorption spectroscopy, because the emitted light in the 90-degree is the maximum, with light intensity. The second thing, it is quite a much free from, not 100% free from, it is quite a much free from the refracted light, transmitted light, other scattered light, etc., etc. So, that is why you are measuring. I hope this basic principle is understood well, so that I can move to the next part of it. Now, we will not look into the principle again anymore. So, you have what excitations and then emission. I will explain more details of this in the next slide, but for the at the moment you can take, this is the molecule called quinine, which is used as a standard or a reference for the fluorescence. So, this particular part is a excitation spectrum and this part is a emission spectrum. This is for the tryptophan. So, I showed you earlier, you can have an excitation. This particular thing is excitation process, this particular thing is fluorescence process, this particular thing is phosphorescence. So, all these three are captured in case of this in this tryptophan. So, tryptophan excitation is coming around 270, around that time. The fluorescence is coming around 330, 340, maybe 350 kind of thing, and the phosphorescence is coming around 450 to 500 range. So, you can see that the excitation wavelength is less than that of the fluorescence wavelength, is less than that of the phosphorescence wavelength. I have been explaining by showing the slide. Please focus the slide on this. So, if you look at the energy gap, as you have seen on the earlier slide here, so this energy is the greater and this energy is less, this energy is much less. So, therefore, the energy of the excitation is greater, energy in kilocalories, kilojoules is greater than that of the fluorescence, greater than that of the phosphorescence. Wavelength wise reverse. So, excitation wavelength will be less than that of the fluorescence wavelength, less than that of the phosphorescence. I hope you understood. And while explaining the Jablonski, I have also talked to you that the fluorescence emission process is challenged by many other, and these are essentially the processes of intersystem, external conversion, internal conversion, some kind of a vibrational, higher vibrations called predissociation, higher electronic states called dissociation. That means when you have a very high energy electronic state is being populated, then you have the breaking of the bonds, etc., all of these. So, if you take rate of each of this with the corresponding K, so K of the fluorescence in the numerator and the denominator, all the other processes, and this is the fluorescence efficiency or quantum yield. You can use any other term and multiply with the 100 will give percentage wise. So, quantum yield, fluorescence efficiency, all of these can be expressed in the fraction value, which will be 1 or less, or in the percentage value, which is the 100%, if it is the best. If there is nothing is making here and the completely fluorescence, no obstruction happening, then it is 100% kind of thing. Okay, of course, these are all compared with respect to the standard reference kind of things as well. Now, let us look at, so what are the kinds of the factors that influence this quantum yield? Type of transition. I will be explaining soon. Type of transition means whether it is a transition of your absorption pi to pi star, then return is pi star to pi, n to pi star, then the return is from pi star to n. The n to sigma star, if it is, then the return is sigma star to that. Sigma to sigma star, then the return is from the sigma star to sigma. So, all of these are called the type of transitions. Okay. Then in the molecule you have a conjugation. In the molecule, whether you have a structural rigidity or flexibility or geometry or planarity, variety of these things. So, all of these things can influence your emission process. They may enhance your emission, they may quench your emission. So, therefore, these are all the factors which affect your emission process. The temperature, the low temperature, room temperature, high temperature. So, those will also, because you will have various vibrational things, rotational things, translational things, etc. So, all these collisions, so they will also make solvent polarity, and whether it is a highly polar, less polar, non-polar, all of these things will also quench or enhance your excited state. So if it is quench the excited state, then you will have a less in fluorescence. If it is try to stabilize the more of the excited state, then you will have more of the emission process. So emission process or fluorescence quantum yield may increase, may decrease depending upon what is happening to the excited state by changing the polarity. What is happening to the excited state by changing the temperature? What is happening to the excited state by changing the your structural rigidity, etc., all of these. So similarly, viscosity, pH, concentration, all of these. Concentration of the species, the low concentration to the high concentration, etc. Various chemical aspects. So some kind of a groups, donor groups, acceptor groups, or some kind of a heavy atom. So all of these can influence your the transition coming from the excited electronic to the ground electronic, and some of the processes will take away the energy in the form of heat, which you will not measure. That means your fluorescence efficiency will be decreasing, or your emission efficiency will be decreasing. Okay, so then also within the molecule or between the molecules, charge transferring occurring. In fact, in inorganic complexes, we have already looked at in the previous case the ligand to metal charge transfer, metal to ligand charge transfer. All of these will also influence your fluorescence efficiency process. So many things. So I just put some points about a 10, but this is not just these alone, but many things can influence your process of the fluorescence. So therefore, fluorescence quantum yield, quantum efficiency, fluorescence efficiency is an indicator to look at the what kind of a process are going on. So many times they will explain whether a complex is formed, whether some recognition process is taking place, whether some changes happened, etc. So therefore, by looking at not only the position of the emission, but also looking at the intensity, quenching, enhancement. So we call increase and decrease as fluorescence enhancement, and so these terms are used very often, means increasing in fluorescence or quantum yield, and then quenching. So the quenching means, so there is decreasing in the fluorescence or decreasing the quantum yield. So that is what is quenching. So complete quenching means completely going down to zero kind of thing. Quenching could be different levels of it. So I hope these basic parameters are very clear. Then it becomes easy to understand the other. So before we go look into the little bit more nature of these transitions, etc., let us look at, I told you earlier, the excitation spectrum, then the emission spectrum, then the phosphorescence kind of thing. Here it is shown for anthracene molecule, you know that, highly conjugated ones in an alcohol. This is the excitation spectrum, and this is the emission spectrum. How is this measured? In this case, you can fix the measuring wavelength, but keep changing the excitation wavelength. So by changing the excitation wavelength, but you measure the emission at a fixed wavelength, you get this one. So that means you are getting the absorption process of various absorption processes from one to the higher electronic levels versus the higher the vibration levels, and that is what is called the excitation spectrum. Now emission spectrum, how you do it? You fix your excitation wavelength, fix, and now you measure emission at various wavelengths. So now if you look at this, one small little increase, then higher, lower. So it looks like if you put a mirror here, you can see there is a kind of a mirror image. So well resolved spectra, you can always see that the excitation versus the emission spectrum will be like a mirror image kind of a thing. Well resolved cases you can always see. This is for some other molecule, you can see 3 and then 3 exactly in that. So now I hope you got it. In the excitation, you fix the measuring wavelength and excite at different wavelengths and measure at a fixed wavelength. That is called excitation. Is what you are doing in excitation. You are taking the pieces of the electronic ground state, populating the excited electronic state, different vibrational levels of the excited electronic state. So that is what you are getting here. Here what you are doing? You are looking at the emission coming from the ground vibrational level of the excited electronic state to different levels of the ground electronic level, and that is what you are looking at. So therefore you fix the excitation process, not the emission process. So emission wavelengths are varied, and this is what that should be very clear. Now, I can do such kind of a measurement, one excited wavelength. I will shift the excited wavelength, again measure the fluorescence, again shift the wavelength and again measure it. So, a different lambda excited. Okay. So, I can make 1 and excitation 2, excitation 3, etc. So, at each case I will get my spectrum. So, if I add all these spectra, and that is what is put over here. So, here one, the other. So, what is the difference between this spectrum and this spectrum? Excitation wavelength is different, nothing else is changed. So, on this one emission wavelength, on this one excitation wavelength. So, therefore, it is a contour. So, it's a profile of so many spectra put one over the other. Okay. And this is I have already explained to you earlier, the light, the sample and the measurement is 90 degree here, and that is what it tells you. So, here, so using such kind of thing you can get the excitation spectrum. I am sure you are now not confused. Your detection wavelength is fixed, excitation wavelength is changed, that is the excitation spectrum. In the emission spectrum, your excitation wavelength is fixed, emission wavelength is changed. So, excitation and emission spectrum. So, that is where you have. So, this is the kind of so you when you put all of these spectra, each one is one measurement. These at one lambda excited, this another, this another, this another, etc. You keep changing the lambda excitation, and that is what is plotted in this axis, and this is plotted on the x axis, and the y axis is your z axis is your intensity. So, x axis is the emission wavelength, y axis your excitation wavelength, z axis is your the intensity. Okay. And that is what you have. So, I mentioned to you that various types of absorption transitions are possible. We studied during the previous topic on the absorption spectroscopy, the sigma to sigma star, sigma to pi star, n to pi star, pi to pi star, etc. Now, in the emission you are looking at the reverse of that. So, in those things the best possible or highest intensity comes from when it comes from the pi star to pi as compared to pi star to n. Because if you look at the pi to pi star transitions, and if you look back into the lectures that I have given earlier, you may have already done some homework, you know that their absorptivities, epsilon values are much greater than the n to pi star or even to n to sigma star. So, it could be even 100 times, 1000 times greater. And second thing is that in such kind of a transitions you have a greater lifetime, something like -5, -6, etc. Whereas for the fluorescence, for the pi star to pi, these are between 10 power -7, -8, -9. So, therefore, that process is much more efficient in term in the fluorescence process of that. So, pi star to pi is much better than the pi star to n or pi star to sigma. Similarly, sigma star to other ones you can do that. So, it is because of their absorptivities are high, because of their the lifetimes are shorter in case of pi star to pi and longer in terms of the pi star to n. These are the kinds of things. So, if it comes from the pi star to n transitions can kind of through coupling can go even to the triplet state. That means you can have a better quenching of the fluorescence. So, that populates the triplet state, that means that will populate the emission from the triplet state which is known as the phosphorescence. Okay. So, if you have the n to pi star to n kind of a return transitions, they may also probably lead to even to the spin orbit coupling through the triplet states. So, these are the different kinds of transitions. So, so the absorption basis, those which have got a higher epsilon value, they return back their efficiency is more. Those the processes which take much shorter time will also help the emission process. Those will take longer time in the excited state. That means they will undergo the collisions, they will lose their energies by thermal, therefore their activities, their fluorescence intensities will go down also. So, I think what I have now focused in this particular lecture is absolutely the rock basic concepts of the fluorescence spectroscopy, and in the next class onwards, next 2 to 3 classes, I will be explaining the examples So, these things you should be familiar to understand those examples of it. Thank you very much.